Grab a pebble, any pebble. Hold it in your hand. Feel the weight of it. Dull, cold, unremarkable. Just a chunk of rock. And if I told you that inside that pebble is a fire more violent than the surface of the sun, you would think I had lost my mind. But I have not. The fire is there. It is inside that pebble, inside every drop of water, every bone in your body, every atom you have ever touched. And the disturbing part is not that it exists. The disturbing part is what you must do to release it. You must break something absurdly small. And when you do, you discover that matter, the stuff you thought was solid and real, is not what you thought it was, not even close. Let me start with the atom. You have heard the word, everybody has, the building block of matter. And the first thing you need to know is that the name is a lie. Atom comes from the Greek atomos, meaning indivisible. But atoms can be divided. They can be split. And when you split them, you find something nobody expected. But first, how small is an atom? Take an orange. Expand it until it is the size of Earth, 8,000 miles across. At that scale, each atom inside would be roughly the size of your original orange. That is atomic scale. If you lined atoms up side by side, you would need 10 million to span a human hair. For most of history, nobody knew atoms existed. It was not until the early 1900s that Einstein proved they were real using Brownian motion. And once physicists knew atoms were real, they asked the dangerous question, what are atoms made of? Here is where things get strange. An atom is mostly empty space, absurdly empty. The outer region is an electron cloud, light particles with negative charge racing around in a probabilistic haze. And deep in the center sits a nucleus, a tiny, dense, positively charged core containing nearly all the mass. If an atom were a football stadium, the nucleus would be a marble at the 50-yard line. The electrons would be insects flying around in the upper deck. Between them, nothing, void. That is what you are made of. Vast emptiness with a tiny, screaming hot kernel in the middle. Ernest Rutherford discovered this in 1911 by firing particles at gold foil. Most sailed straight through because the foil was mostly empty, but occasionally a particle bounced straight back. Rutherford said it was like firing a cannonball at tissue paper and having it rebound at you. That was the nucleus, tiny, dense, harder than anything imaginable. So the real story happens inside that nucleus. The nucleus contains protons, which carry positive charge, and neutrons, which carry no charge, both roughly 2,000 times heavier than an electron. And they're crammed together in this absurdly tiny space. If you could collect a teaspoon of pure nuclear matter, it would weigh 10 billion tons. A teaspoon, 10 billion tons. Immediately, there is a crisis. The protons are all positively charged, and positive charges repel violently. The electromagnetic force is trying to detonate the nucleus. Every instant, the protons are screaming at each other to separate. So why has the nucleus not exploded? There must be another force, something stronger. And there is. We call it the strong nuclear force, roughly 100 times more powerful than electromagnetism at close range. It grabs protons and neutrons and locks them together. But the strong force has a peculiar property that determines the fate of every nucleus in the universe. The strong force only works at extremely short range. If two protons sit right next to each other, the strong force holds them magnificently tight, but move them apart by even a few femtometers, a few millionths of a billionth in a meter, and the strong force drops to zero, gone. Meanwhile, electromagnetic repulsion has much longer reach. In a small nucleus like helium, with just 2 protons and 2 neutrons, everything is fine. Everyone is close. The strong force grips all 4 particles. The nucleus is stable. But as you add more protons and neutrons, the nucleus gets larger. Now you have protons on opposite sides, sitting far apart. The strong force between them? 0. But electromagnetic repulsion? Still there, still pushing, still trying to tear the nucleus apart. So in a large nucleus, you have warfare. The strong force holds neighbors together. Electromagnetic force pushes all protons apart. As the nucleus grows, the electromagnetic side gains ground. The nucleus becomes fragile, volatile, like a water droplet stretched too far, ready to break. This competition explains everything. Physicists measure binding energy per nucleon, how tightly each particle is held. If you plot this for every element, you get a curve. It peaks at iron. Iron is the most stable nucleus in nature. Think of this curve as a valley with iron at the bottom. Elements lighter than iron sit on one slope. Elements heavier than iron sit on the other. And nature wants to roll downhill toward iron. For light elements, rolling downhill means fusion. When hydrogen fuses into helium in the sun, energy releases. That's sunlight. For heavy elements, rolling downhill means fission. When uranium splits into smaller pieces, energy releases. Fusion rolls down one slope, fission down the other. Both head toward iron. Both release energy. Now let me split an atom for you. In the 1930s, physicists were firing neutrons at elements to see what happened. When they hit uranium with neutrons, strange things occurred. In Berlin in 1938, Hahn and Straussman bombarded uranium and found barium, an element with only 56 protons, roughly half uranium's size. How could you throw a tiny neutron at a uranium and get barium? It was like tossing a pebble at a boulder and having it split in half. Hahn wrote to Lise Meitner, a physicist in exile in Sweden. She and her nephew, Otto Frisch, worked through the physics over Christmas. They realized the uranium nucleus had absorbed the neutron, become unstable, and literally split in two. Meitner calculated the energy release using Einstein's equation and got a number that made her hands shake. About 200 million electron volts per split. Frisch named it fission after how cells divide, and the world changed. Here's what happens. Take uranium-235, 92 protons, 143 neutrons, jammed into a space a few femtometers across. A big, heavy, unhappy nucleus barely holding together, vibrating like a water droplet on a hot skillet. A slow neutron drifts in and is absorbed. The nucleus becomes uranium-236. That extra neutron tips the balance. What happens next takes 100 billionth of a trillionth of a second. The nucleus deforms, stretches into an oval. A waist forms in the middle like a peanut. The strong force across that neck loses grip. Electromagnetic repulsion wins. The neck narrows, then snap, it tears. Two fragments fly apart at 3% light speed, typically barium and krypton, along with 2 or 3 free neutrons and gamma rays.
But here is what disturbs me. If you carefully weigh everything before and after, the total mass afterward is less, by about 1/5 the mass of a proton. But it is real, measured, undeniable. Mass has vanished from the universe. Where did it go? It converted. That missing mass became the kinetic energy of fragments, the gamma rays, the heat and radiation. Mass turned into energy. Matter ceased to exist as matter and became pure physical energy. This is E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is 186,000 miles per second. Square that, and you get about 35 billion. That is the exchange rate. A tiny amount of mass disappearing corresponds to enormous energy appearing. 1 pound of uranium-235, fully fissioned, releases the same energy as burning 3 million pounds of coal. 1 pound versus 3 million. The energy was locked inside the uranium's mass for billions of years. Every chemical reaction you have witnessed, every fire, every explosion, rearranges atoms, breaks chemical bonds, and forms new ones. The difference comes out as heat, but in chemistry, the nuclei are untouched. A chemical explosion converts about 1 part in a billion of mass to energy. Nuclear fission converts 1 part in 1,000, 1,000,000 times more efficient. A raisin weighs about 1 gram. E equals mc squared tells you 1 gram of anything contains about 25 million kilowatt hours, enough electricity to power an average home for 2,000 years, from a raisin. Fission unlocks about 1/10 of 1% of it, and even that tiny fraction can power cities or destroy them. Now here is the terrifying part. Those 2 or 3 free neutrons that shot out when uranium split. If other uranium nuclei are nearby, those neutrons can trigger more fissions. Each fission releases more neutrons. 1 becomes 2, 2 become 4, 4 become 8. The number doubles every 10 nanoseconds. After 80 generations, roughly a microsecond, you have 10 to the 24th fissions happening simultaneously, each converting mass to energy, all in a space the size of a grapefruit. That is a nuclear explosion. The chain reaction is self-amplifying. Nature provides the amplification. All you need is enough material assembled quickly enough. The physics is straightforward. 1 neutron starts it. The process feeds itself. You give nature 1 event. She gives you 10 to the 24th. There's a threshold called critical mass. For uranium-235, about 115 pounds. Below it, the reaction dies. Above it, it runs away. The difference between a paperweight and a nuclear explosion is a grapefruit's mass. But there is also a peaceful version. In a reactor, you control the chain reaction, so each fission triggers exactly 1 more. The reaction sustains at constant level, converting mass to energy steadily. You use control rods that absorb excess neutrons. Pull them out, the reaction speeds up. Push them in, it slows down. The same process that destroys cities can generate electricity to light them. The physics is neutral. What you do with it is human choice. This is what disturbs me most. We trust matter. We trust the floor not to collapse. We trust our bones to be solid. But matter is not what we think. Matter is energy in disguise. Energy frozen into configuration, locked by balanced forces, sitting quietly like a compressed spring, carrying enormous potential. The pebble in your hand is not inert. It is an energy warehouse so vast that Earth's largest coal deposit looks like a spent match in comparison. We are surrounded by frozen energy. We are made of frozen energy. The only reason the world seems calm is that releasing it requires specific conditions. The nuclei in your body have been intact for 4.5 billion years. The strong force does its job, but the energy is there, always there. The fire does not go out just because you cannot feel the heat. Everything you see, everything you touch is actually a balance between forces. The strong force holds nuclei together. Electromagnetism pushes them apart. The balance holds for billions of years, but it is always a balance, always a truce, and truces can break. So tomorrow, when you pick up any object, a coffee cup, a pen, a child's hand, Hold it for a moment. Know that what you are feeling is not simply stuff. What you are feeling is energy, a staggering amount of energy, bound so tightly it behaves like a solid, permanent thing. But beneath that calm exterior is a fire that has burned since the first atoms were assembled in dying stars, a fire older than Earth, a fire that will outlast everything you know. You are holding it right now. You are made of it right now. Frozen fire pretending to be a person. Tell me, now that you know what that pebble is actually made of, does the world feel different in your hands?